Hey everyone, and welcome back to our flipped classroom for chemistry. Today we're discussing uncertainty and significant figures. So uncertainty and significant figures, our focus is really all about understanding what we can know about measurements, what we can't know about measurements, and how we communicate that information to someone who might simply be looking at those numbers, at those measurements. So there's always going to be limitations in our measurements. There's always going to be some uncertainty. And so we talked about when we take measurements that we're always going to estimate a digit. And that even if we're looking at a digital readout, we understand that the last digit is always going to be estimated and there's going to be some uncertainty. So we always want to be able to communicate that uncertainty. And the the more decimal places we have, generally speaking, the more precision we have. So let's talk about precision. So we're going to talk about two terms, precision and accuracy, and they are related, but they are not the same. And we use both of these to determine how uncertain a number may be. So when we talk about accuracy, we're referring to the agreement of a value with the true value. So that if we have a standardized weight and we know that it weighs 500 grams and we put it on our balance and the balance reads 500 grams, that balance is very accurate because it's agreeing with the true value. Precision refers to how much our measurements agree. So that would be if we take that weight and we put it on 5 different balances and got 500 on each, then it would be very precise. So those numbers are all close together. So accurate means is it close to the true value, and precise means are the values all close together. So if we were to look at this particular grouping, we would say that these arrows, whoever was shooting wasn't very accurate and wasn't very precise. So we're not accurate nor precise. Here we have a grouping of arrows. They're all very close together. So these are very precise. This was a very precise shot, but if you're trying to hit the bullseye, it was not very accurate. So here we have precise, but not accurate. And then of course, the ultimate goal is always to be both precise, close together, and accurate, close to the actual value. And here we have a grouping of arrows that is both precise and accurate. So let's talk about error and how this relates to precision and accuracy and how it's going to relate to uncertainty. So we can have one type of error is random error. And when we have random error, that means that our measurement has an equal probability of being too high or too low. So this is indeterminate error. This is usually caused by mistakes. And so if we have a bunch of random errors, then even if none of them are particularly accurate, but we've repeated the process multiple times, then we're likely on average to have a fairly accurate answer. When we have systematic error, this means that this is an error that's occurring in the same direction every time. It's either too high every time or it's too low every time. And usually this is a result of poor technique, maybe those parallax errors that we talked about with reading volume, or an incorrect calibration. So if we have systematic error, we may well have very precise values, but we might not have very accurate values. So error and our inability to read things tends to bring in uncertainty. All of our measurements are always going to have uncertainty. Why is that? Because we use instruments. No instrument can read to an infinite number of decimal places, and we have limitations on the human eye. So we can only estimate to a certain number of decimal places. So if we were looking at these two balances, one of them is going to have much more uncertainty than the other. And we can see that this balance on the right reads to 3 decimal places, whereas this one is measuring only in tenths. And so we would assume that the one on the right is much more precise and has much less uncertainty. And we remember from our discussion about how we measure things that we are always going to estimate one digit past the graduation. So that means the last digit of any measurement is always an estimation. And we're going to use these things called significant figures to communicate that information. So we're using those significant figures to communicate the precision with which a measurement was made. All of our measured numbers and one estimated place are considered to be significant. So just as you're seeing in the measurement activity, this beaker is only graduated in tens, and so we would be able to estimate to the ones place. But this flask is only measured or graduated in 25, so we would be able to estimate that it's somewhere between 25 and 50. Maybe we could estimate in fives, but probably not in ones. Whereas our graduated cylinder is graduated in ones, which means we're going to be able to read it to the tenths place. And finally, we have a burette that is graduated in tenths. So we're going to be able to estimate to the hundredths place. So we have 4 different devices. We would have varying degrees of precision, and therefore we would have a different number of significant figures in each number, even if we were using the same amount of water in all 4 of these devices. So significant figures, their job is just to communicate precision. We use them when we are just communicating a number. We might not say that we used a graduated cylinder or a burette or a flask or a beaker, but by looking at the number, the scientist on the other end is going to be able to tell how precise the instrument was. So we're going to look at some rules for counting significant figures. So our first rule, non-zero integers always count as significant figures. So if we're looking at this number, 3,456, it has 4 non-zero integers, so it has 4 significant figures. Zeros are when it gets a little bit interesting. So leading zeros, these are zeros on the left-hand side of the number, and we generally only see these when we have a decimal. Leading zeros do not count as significant figures. Let me say that again. Leading zeros never count as significant figures. So if we look at this number, 0.0486, these are leading zeros. They do not count. This has only 3 significant figures. Now let's look at zeros in the middle. So zeros we call captive zeros. These are zeros between 2 integer digits. So 16.07, that 0 right there is in the middle between a 6 and a 7. This is a captive 0. It has 4 significant figures. So this is telling us that this instrument that we used was graduated to the tenths and we estimated the hundredths. One more rule about zeros. Trailing zeros are significant only if the number contains a decimal point. So the number 9.300, those are zeros after the decimal place. They are not leading zeros, they're not at the front, they are trailing zeros, and so they are significant. This has 4 significant figures. So again, whatever instrument we used to measure this was graduated to the hundredths place, and we're estimating the thousandths place. The job of the significant figures is to communicate information about the precision of the instrument that was used to make the measurement. One last rule for counting significant figures. There are these things called exact numbers, and exact numbers have an infinite number of significant figures. So there are 2 ways to have an exact number. Something that is counted, okay? In one class, I have 9 students. In another class, I have 15 students. There is no question. I can count the students. I know that there are exactly 9 or there are exactly 15. Those numbers have an infinite number of significant figures. So that means when it comes to using them in a math problem, they don't impact the problem at all in terms of significant figures. The other type of significant figure, our exact number, is a conversion factor. And Conversion factors within a system are always exact, and some conversion factors between systems, so 1 inch to 2.54 centimeters, is an exact number. And that will come into play when we talk about how we do math with significant figures. All right, so we're going to practice. I'm going to have you pause this each time, and we'll look at how many significant figures there are. So here we have, this is significant. These zeros are captive, so these zeros are significant. That's an integer, so that's significant. And that's a 0 after a decimal place, so it's significant. So this number has 5 significant figures or sig figs. So for the rest of these, I want you guys to pause and then check your work. So we have 17.10 kilograms, 4 sig figs. 100,890 liters has 5 sig figs. 3.29 times 10 to the 3rd seconds has 3 sig figs. And 0.0054 centimeters has only 2 sig figs. Oh, one more. 3,200,000 has 2 sig figs. All right. So now rules for what we do in mathematical operations. We'll start with the easy one. When we are multiplying and dividing, the number of significant figures in the result is the number of significant figures in the least precise measurement used in the calculation. So you're going to count the sig figs in both of your numbers. Whichever one has fewer, that's how many your answer can have. So if we have 6.38 times 2.0, when you put this in your calculator, it's going to give you 12.76. And that is the number 13, and that has only 2 sig figs. And we'll practice these in class. So here's the one that's a little bit more challenging. Addition and subtraction. The number of decimal places in the result is equal to the number of decimal places in the least precise measurement. Notice now that we're not counting significant figures, but decimal places. So if we look at 6.8 plus 11.934, this number is less precise than this number because this one is only estimated in the tenths place. This one is estimated in the thousandths place. So we're going to add these two numbers together, but we're going to recognize that the tenths place is where our number has to be rounded. So we get 18.734, and we're going to round it to 18.7, which will give us 3 sig figs. Okay, as always, if you have questions, please write them down, let me know, and we'll go over them in class, and we will do lots of practice with significant figures in class.